So let's now talk about votes and Bayesian combination. So the point with voting here is to simply assign if we are talking about classification, we have basic classifier, we will assign a sample to the most frequent class among the basic classifiers. We can generalize this with some kind of weighting. Here we have a weight for each voter. So if we are putting ourselves in the context of binary classification, every HJ here, that we see here, is the binary decision of like, is it from the positive class or negative class? So we can get something like 1, 0 or 1, -1. Both are okay in that formulation. So we have a basic decision that is positive or negative or +1 or 0. And we are weighting this through the weight WJ. So this is a factor that can be stated at first. For example, saying we put more weight, so we assign more values to a given member or not, or we can reduce that value. So, and we are summing this, we are summing the weight times the decision, which should be 0, 1 or -1 +1. And we know that we are constraining these weights to sum to 1. We just want to get a bunch of values that are summing to 1 in terms of weighting for the different models. So this is basically a linear model for parallel combination. And in the case of simple voting, the voting that we are used to, saying that everyone has equal weight, or I would say every vote count for the same value. It's simply like using WG equal to 1 over L. So we just assign the equal weight for every voter, every model used here. So the weights can represent somehow the confidence in each classifier. So if we know that some classifiers are better than others in a given X, we can increase that WG accordingly. Or we can just say it's the general confidence. We know that classifier is particularly performing well in general, so it can has a bigger weight than another one which is poorer. So the model in terms of voting goes with this. We simply have a X data. We assign this X to the L voters, L classification, binary classification models here. So we just have L different models, which can be anything, you know, what we saw so far. And then we get the decision from each of these L models, and we multiply this by the weight W, and we sum this, and it gives us the H bar, which corresponds to the ensemble decision. We can, in fact, refer that as completely in line with what we saw before in terms of Bayesian decision models, Bayesian models. So, you know, here it's basically to state, okay, the probability of assigning to class CIX. So we have our posterior probability is corresponding in an ensemble model to the sum over all models of the decision per model. So this is basically the decision to assign to class CIX for classifier MJ. And we multiply this with the prior, which is the prior probability on model J. And this prior can be explained somehow as the weight or the expertise or the relevance of a given model for this ensemble decision. So we have WJ that can be stated as basically the prior over the model MJ. And we have the H, which can be here simply the posterior probability of that model over the sample X. So simple voting is basically a case for an a priori equal probabilities. Basically, PMJ is equal at 1 over L. So now if we look at the bias and the variance in the two-class classifier ensembles, we can assume that the decision are RID. It's still strong, but you know it's good for simplifying the developments and getting some insights on how it works. So looking at basically the expectation over the output, we can look at some of the expectation over the sum for the L members here. So we need this because we want to develop the bias and the variance of the ensemble. So basically the expectation of a sum like this, we can simplify this like that and basically state that in fact, given that our models are RID, the expectation of the ensemble is corresponding to the expectation of each members. And then we can look at the variance. And this is where the interesting things are. The variance over the ensemble correspond to the variance over the ensemble decision. But now in terms of simplification, you know, it's like 1 over L squared times L. And basically it boils down to 1 over L times the variance of individual members. That means that the ensemble variance is about 1 over L times the individual variance. So we have a much lower ensemble variance than individual variances. So the variance decreases as the number of independent voters increases. So the point is that we just by increasing the number of members, we can expect to reduce the variance without affecting the bias. So the bias will stay the same. Given that our models are RID, we will not reach any lower bias, but we will reach much lower variance in our decision, given that we are voting, averaging over many models decisions. And as such, given that we are able to reduce the variance, the quadratic error, the whole mean square error, least square error will be reduced accordingly. Now let's move back. Let's say in general, let's look at the ensemble variance. And now let's not assume that they are IID. Let's assume that there can be some kind of correlation between the members, which is existing. So we are removing the IID hypothesis. And we say, okay, let's look at the ensemble variance, which is basically this thing here, which is not that different. But the point is that if we develop this thing, the variance over the summation of HG, it is equivalent to summing somehow the variance of every members, but given that we are dividing by 1 over L squared, that's okay. It's basically averaging, but multiplying by 1 over L as what we have before, because, you know, this thing corresponds to what we had in the last slide. The new addition is that part, which is basically the covariance between different members. That's because they are no more independent. If we assume they are not independent, they have some kind of covariance. And we are looking at summing this covariance over every pair. So every pair of HJ, HI will get its covariance computed, and that will be a component of the ensemble variance. So the trick is to say, if we are able to somehow reduce the correlation between the voters, if we can get them anti-correlated, if we can reduce their correlation, the variance will be reduced accordingly. So that's, I would say, a nice insight to say, how should we generate our members in terms of having better performances? And this will lead for, in terms of regression, you know, it's not in terms of classification, but in terms of regression, we will get lower quadratic error, least mean square error, provided that the negative correlation does not affect the bias of the set. That's really important, because as we increase this, as we get, I would say, some kind of negative correlation here, you know, it may affect the bias. And this is bad, because at some point, you know, the effect on the bias will be much stronger than the effect on the variance. So diversity here is the answer. In our ensemble, we want an ensemble that is diverse. So the goal in the overall training is to obtain classifiers that do not make the same mistakes on the same sample. And the point, you know, if we go at extreme cases, extreme cases will be L copies of the same classifier. This is worthless, because if this is a copy of the same classifier, all the decision will be the same for all samples. You know, we'll get all ones for a given sample, all zeros for the other samples, because these are the same model. So this is an example of extreme non-diversity. Yeah, so we need to be sure that we get some kind of diversity in our ensemble to obtain good results.